Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is module 15 in my probability and stochastics process lecture series where I talk about the exponential random variable. Now, in a way, and this is, kind of lighthearted, I suppose, but in a way, I think of the exponential random variable almost as the Gaussian distribution or the Gaussian noise of networks. And the reason why I say that is because in my electrical engineering education, it was the Gaussian distribution that seemed to have the starring role. So because it was present, it's used to represent thermal noise in electronics, noise in communication systems, and certainly my background is physical layer wireless communications, and it always seemed like we were working with some sort of distribution that was based on the Gaussian distribution. So for example, in wireless channels, the distributions that we sometimes use to model fluctuations in received signal power, the Rayleigh distribution, the Ricine distribution, those are based on or functions of Gaussian random variables. And so we tend to focus on the Gaussian random variable a lot in electrical engineering, but the exponential random variable is also incredibly important, particularly if you're working in the area of networks and network analysis, because as we're going to see, much of of how we model things like traffic flow, queues, backups of packets in router buffers and things like that are all based on the exponential random variable. And so to start things off, we will take a look at the PDF and CDF of the exponential random variable. We did sort of take a look at this early on in the lecture series, but we'll revisit it again quickly. So the PDF of an exponentially distributed random variable is the exponential function, hence the name. It's equal to lambda e to the minus lambda x for x greater than or equal to 0, and the PDF has no value for negative or 0 value for negative values of x. And the CDF one minus e to the lambda x for x greater than or equal to 0 and 0 for x less than 0. So to determine the moments, we can, there's a couple of different ways we can do it, but let's, in this case, use the moment generating function for the exponential random variable, or let's start by defining the moment generating function. So the moment generating a function, as we've seen earlier in the lecture series, is the expected value of e to the sx, where x is our random variable. So this is essentially a function of a random variable. And because we're taking the expected value, we can integrate from 0 to infinity. 0 because the PDF is only non-zero for positive values. And then we can use the expression g of x multiplied by the PDF, as we've seen. In this case, our function is e to the s x. Now we're working with little x because that's our variable of integration. Lambda e to the minus lambda little x dx. We can take the lambda out front, merge our exponential terms. So we have e to the minus lambda minus s x dx. And of course, solving that integral's straightforward. Lambda minus s for values of s less than lambda. And that constraint's not a big deal, because if you'll remember, when we use the moment generating function to determine moments, we set s equal to 0, and for most applications, meaningful applications, lambda will be greater than 0. And so using our moment generating function, we can determine the mean of the exponentially distributed random variable. That's equal to the first derivative of the moment generating function, where we set s equal to 0. The first derivative is equal to lambda over lambda minus s squared. We set s equal to 0, then we get 1 over lambda, as we saw earlier on when we introduced the exponential random variable in our earlier modules. The expected value of x squared, of course, is the second derivative of the moment generating function. S equal to 0. In this case, we have 2 lambda over lambda minus s cubed. Oops. Again, s equal to 0. And this is equal to 2 over lambda squared. And then if we want to determine the variance of our exponentially distributed random variable, the expected value of x squared, whoops, not equals, minus the square of our mean. So 2 lambda squared minus 1 over lambda squared. So the variance is 1 over lambda squared. Now, one of the most important properties of the exponentially distributed random variable, and one that we're going to be using quite a lot in our coming discussion, is the memoryless property of the exponential random variable. And the best way to understand the memoryless property, or the novelty of it, is to introduce it kind of with an example. And so basically, if let's say we have the a device, a car, a piece of electronics, something like that, that has an exponentially distributed lifetime. So the time to failure is exponentially distributed. And this is something that has been shown to hold for a lot of different devices. Now, the memoryless property basically says that the probability that an old item lasts a certain period of time is exactly the same as a brand new item lasting that same period of time. Or if we want to be precise about it, the probability of our exponential random variable being greater than s plus t, oops, I'll use a different color, a little more clear. The probability of our random variable being greater than s plus t, given that it's already greater than t, is just the probability that our random variable is going to be greater than s for all positive values of s and t. And so this is best understood as using an example. So this basically means that let's say we've got a car with an exponentially distributed lifetime with a mean lifetime of 10 years. And what we're going to do is we're going to calculate the probability first that a brand new car lasts for 15 years. And then we're going to calculate the probability that a used car that's 5 years old also lasts another 15 years. And the memoryless property is going to basically mean that these two probabilities are going to be exactly the same. And so let's start with the brand new car. And so we know that the mean lifetime of our vehicle is 10 years. And we know that the expected value of an exponentially distributed random variable is equal to 1 over lambda. This is equal to 10. And so that means lambda is equal to 1 over 10. Now, the probability that our lifetime is greater than 15 years is just equal to the integral of 15 to infinity of our PDF. And so the probability is 22%. And this comes from the fact that in general, the probability of an exponential random variable being greater than some value alpha is equal to e to the minus lambda alpha. And so if we take a look at our used car now, so the probability used car lasts 15 more years is basically equal to the probability that our exponentially distributed lifetime x is going to be greater than 20, given that we know for sure our lifetime is going to be greater than 5, right? Because it's already lasted 5 years when we bought the used car. And so using the formula for conditional probability, this is equal to the probability of our exponential random variable being greater than 20 and the exponential random variable being greater than 5 divided by the probability that we're greater than 5. Of course, the probability of x being greater than 20 and being greater than 5 is just the probability of x being greater than 20, because the second event is a perfect subset of the first. And so this just ends up being equal to x greater than 20 divided by the probability of x being greater than 5. Using the results from the previous slide, this probability is e to the minus 20 alpha divided by e to the minus 5 alpha, which is e to the minus 15 alpha, or 22%. And we can, which is the same as the new car. And of course, we could have proved this in the general sense. So the memoryless property in general is the probability of x being greater than s plus t, given that we know that x is greater than t. Just going through exactly the same steps as in the previous example. X greater than t. And if we write this now in terms of our exponents, minus lambda s plus t divided by e to the minus lambda t, e to the minus lambda s plus t plus lambda t, which is just equal to e to the minus lambda s, which is the probability of x being greater than s. So this proves the memoryless property in general. And as I said, this is going to be a very useful property that we're going to take advantage of quite a bit in the coming discussion. And it's often kind of, when students first sort of look at this, it's kind of mind-blowing in a way, because this basically says there's no reason to buy a new car. Right? So the probability of your used car giving you 15 years of service is exactly the same as the probability of the new car. And so what's going on here? Well, the reason why this is the case is because often when a car rolls off of the factory floor, if there are any manufacturing defects, those tend to show up fairly early on in the lifetime of the vehicle. And so even though, eventually a car will wear out just from use, if you buy a used car, chances are all of those early factory defects have already sort of been shown up and fixed, or the car has been removed from the population of cars because it's broken early on. And then if you buy a used car, you've got a vehicle that didn't have any manufacturing defects, and it is going to last a little bit longer, but will eventually wear out just because of just general wear and tear. Now, is this universally true? Does this mean that you could buy a 50-year-old car and expect another 50 years of service, just like you could from a brand new car? Probably not. And the reason why not is because, the lifetime of vehicles and manufactured products in general, while, generally they follow an exponential distribution, eventually there's deviation from the distribution, particularly very far out in the long tail of the exponential. But still, it is a property of the pure exponential distribution. And as I said, this is something that we're going to be using a fair bit in the coming discussion. So another property that we're going to be using later on is the distribution for the sum of exponential random variables. And so we're going to consider two cases when we add together exponential random variables that all have the same rate, the same value of lambda, and the case where we add random variables when they all have different values of lambda. And so let's consider the first case where all of the random variables in the sum have the same value of lambda. So if we add n random variables together, the PDF for the sum of the random variables ends up being equal to the gamma distribution, where n is the number of random variables we're being added together, and lambda is the common value of lambda that they all share. There's a couple of different proofs for this. They're fairly involved. I'm not going to go through a fully rigorous proof. Instead, what I'm going to do is I'm just going to give you an example of adding two random variables together. We'll do the convolution and we'll show that, at least for the case of 2, it equals a gamma distribution. And then you can sort of continue the proof from there if you like, but there are other ways to do the proof as well. So let's consider two random variables together. So the overall PDF is equal to the convolution of the PDF of x1 and the PDF of x2. Integrate from 0 to the shift value of our convolution t. We started 0 because the PDFs are equal of the exponential random variable are equal to 0 for negative values. And so if we just plug in our PDF values, pull our lambdas out front. And we can pull one exponential term that's a value of t out front. We integrate 0 to t, but we have a negative lambda s in our exponent in the first exponential, and we actually have a positive lambda s because the two negatives cancel. And so this ends up being equal to 1 ds, and we end up getting lambda e to the minus lambda t times lambda t. And of course, this is equal to 1 divided by 1 factorial. And so this is the gamma distributed, or the gamma PDF, or the PDF of a gamma random variable for n equal to 2. Now, if we add the rates of, oops, there's a little bit of a typo in there. When the rates of exponential random variables are all different, the sum of those exponential random variables is what we refer to as a hypo-exponential random variable. And again, what we'll do is I'll show you the PDF for adding 2 random variables together, and that's going to suggest a generalized form, which I'm then going to give to you. I'm not going to go through the full rigorous proof, again, because it gets into a little bit too much detail, but it's easy to find if you are interested in the proof. So for a sum of 2 random variables, again, we have f of t 0 to t Now we have lambda 1 and lambda 2. Oops, that should be lambda 1. This is lambda 2. ds. We have lambda 1 times lambda 2, oops, e to the minus lambda 2t, 1 minus e to the minus lambda 1 minus lambda 2 t. And then if we just put this in kind of a more generalized form, just doing a little bit of algebra, we have this final form. So we have lambda 2 e to the minus lambda 2t plus lambda 2 over lambda 2 minus lambda 1, lambda 1 e to the minus lambda 1 t. And so this solution just for 2, the addition of 2 random variables, suggests kind of a general form where we have a term where we have the rate of, or the lambda value for the random variable multiplied by e to the minus lambda value t, multiplied by a coefficient and then added up to all the other ones. And that is indeed what we have. So if we increase n, it can be proven by induction, basically. So starting from 2 and then going to 3 and so on, that the general PDF for the hypoexponential random variable is in fact a summation where we have the individual PDFs multiplied by a coefficient, and this is the coefficient value.